Okay guys, so now we will talk about the series, and to begin with I'm going to tell you stuff that you probably know from calculus 2, but I just want to repeat it, that we're going to take a sequence of numbers, say C0, C1, C2, etc., Cn, etc., and instead of having a comma between them, we're going to put a sign between them. So we're going to write C0 plus C1 plus C2 plus etc. plus Cn plus etc. And this particular expression is called the series. Now be very, very, very careful with the sign in between those series, because there is not really a plus. It is just a sign. Why is it not a plus? Because if you think about it as a plus, you can define the sum of two numbers, but you cannot define the sum only of infinitely many numbers. And if you could, strange thing would happen. For instance, if I look at 1 plus minus 1 plus 1 plus minus 1 plus 1 plus minus 1 plus etc., what is this equal to? Now, on the one hand, I could easily take the series and combine these terms here, and so that will give me 0, and this would give me 0, and this would give me 0, and if life works out right, then the sum of zeros should be equal to 0, and the series equal to 0. On the other hand, I'm going to take the exact same series and now I'm going to put the brackets in a different way. I'm going to put the brackets here and here and here. And so all these terms are going to be 0, and the first term is going to be 1, and therefore the same series equal to 1. So now we have this possibility that if we treat this sign as a regular plus sign, 0 is equal to 1, the life is mathematics is inconsistent, we're all out of jobs, and it will not go any good. Now, just as a side comment, I have to tell you that if you take these two different sums of those series, 0 and 1, so if this series is equal to 0 and this series is equal to 1, then twice the series is equal to 1. And so s is equal to 1/2. Now this is not true. S is not equal to 0 or 1 and 1/2. It simply does not exist. But if somebody puts a gun to your head and say, give me a number, 1/2, as you will see later on, is actually the best possible answer you can give them. And then another strange thing occurs, and that is the sum of a bunch of integers is equal to a fraction. Okay, so the point is that this expression over here, C0 plus C1 plus C2 plus C3 plus etc., is to be treated simply as an expression, and often it is written in a sigma notation, Ck, k from 0 to infinity, and this expression by itself is called the series. Now let me say one more word about sigma notation. You're probably familiar with them. You probably have seen them before, and like any normal student, you prefer to deal with sigma notations because they're shorter than to write down all these terms of the series. To be honest with you, in most mathematical books, everything is written in terms of sigma notation, but most of the mathematicians that I know, when something is written in a sigma notation, they go home, they quietly take the sigma notation. So start here and write this thing as C0 plus C1 plus C2 plus C3 plus etc., just to understand what is really going on. So while I encourage you to understand and be able to deal with the sigma notations, I also encourage you to, for any particular series, to write down a few first terms so that you will understand what really happens. Okay, so now let's start with the definitions. So when I have the sum of ck, k from 0 to infinity. With this sum, or with this series, I'm going to associate a sequence Sn, which is called a sequence of partial sums. So in that case, S0 is equal to C0, S1 is equal to C0 plus C1, S2 is equal to C0 plus C1 plus C2, etc. Sn is equal to the sum k from 0 to n of ck. So the sequence of S's is called the sequence of partial sums. Again, you have to be very careful, because with every series you associate an object called the series, and this is this. You associate a sequence of the terms of the series, so the terms of the series are the C's. And finally, you associate another sequence, which is sequence of partial sums, and this is Sn. And now for the key definition of the subject, the series Ck, k from 0 to infinity, converges if the sequence, what sequence? The sequence Sn, the sequence of partial sum, converges. And so in this way, I reduce the question about convergence of the series to the question about convergence of certain sequence, and convergence of the sequence we studied in a previous class. So this is a definition of convergent series, and so one of two things may happen if the sequence Sn diverges. Then we say that the series Ck, k from 0 to infinity, diverges, and that's the end of the story. There is nothing more to say. We're not going to deal with it anymore. All we can say is that the series diverges, and as you will see later on, in particular those series that I showed you before, this series are going to be divergent series. Okay, so let's check it just for fun. So if I start out with the series 1 plus minus 1 plus 1 plus minus 1 plus etc. So this is the same series as a sum of minus 1 to the power k, k from 0 to infinity. Agree that what's written here and what's written here is the same thing. So now what is my S naught? My S naught is equal to 1. My S1 is equal to 1 minus 1, which is equal to 0. My S2 is equal to 1 plus minus 1 plus 1, which is equal to 1. My S3 is equal to 0, etc. So in this case, the sequence of partial sums, Sn, will be the sequence consisting of 1, 0, 1, 0, 1, 0, etc. And I hope you know that the sequence diverges, and therefore the series minus 1 to the k, k from 0 to infinity, diverges, and that's it. That's the end of the story. There is nothing more to say about this particular series. Now, one more comment. If you have a series Ck, k from 0 to infinity, and if this particular series converges, that means that the sequence Sn of partial sums converges. And if it converges to something, so let's say to S. And in that case, we will say that the series Ck, k from 0 to infinity, is simply equal to S. Okay, so the object of this particular rest of the chapter is to decide more or less easily and quickly when the series converges and when the series diverges. Again, it will not be important most of the time to know what the series converges to. All we care about is to decide whether the series converges or diverges. Good. Okay, so let's start with a few preliminary, very simple results. So suppose that I have a sequence Sn. Now remember, this is a sequence of partial sums. This is a sequence of real numbers, right? And we know from the previous section that this sequence converges if and only if it is Cauchy. We will return to this criteria later on, but for now let me just very quickly remark that means it means that this sequence is Cauchy. It means that for every epsilon greater than 0 there exists an n, such that if n and m are greater than n, this implies that Sm minus Sn is less than epsilon. So what is Sm minus Sn? In case of partial sums, it is actually a nice expression. So suppose that m is greater than n. In that case, Sm is equal to C0 plus C1 plus C2 plus etc. plus Cn plus Cn plus 1 plus Cn plus 2 plus etc. all the way to Cm. Sn is equal to C0 plus C1 plus C2, the same thing, plus Cn, and then it stops here. So that means that Sm minus Sn is equal to Cn plus 1 plus etc. plus Cm. And what I would like to do is I would like to make sure that this converges to 0. In other words, I want to make sure that this sum of ck, k starting at n plus 1 to m, converges to 0. I will return to this criteria in a minute, but let me just say a few general remarks about the convergence of the series. So the definitions that I gave you here before, and of course I'm going to repeat it, is that the series sum of ck, k from 0 to infinity, converges if and only if the sequence, and again I emphasize the word sequence, Sn of partial sums converges. So in principle, I'm saying that when I'm dealing with a series, I'm dealing with a sequence. On the other hand, if I'm dealing with particular sequence, so let's suppose that I have a sequence consisting of numbers a1, a2, a3, etc., and I'm going to form new numbers, or, well, let's start with, I don't know, a0, and I'm going to be dealing with a sequence, with a series consisting of the following numbers. A1 minus a0, so this will be the first term of my series, and then I will have a2 minus a1, and then I will have a3 minus a2, etc. So now, starting with an arbitrary sequence, I'm forming a series. And what are the partial sums for the series? Well, the first partial sum is irrelevant. It's a1 minus a0. The next partial sum, which is s1, will be a1 minus a0 plus a2 minus a1. So it will be a2 minus a0, and then s3 will be equal to, well, let's see, if I add those three, a1 and a1 cancel each other, a2 and a2 will cancel each other, and I will have a3 minus a0. And so my point is that if I start with a particular sequence, the sequence converges if and only if the series converges. Okay, so convergence of the sequence and series are the same thing, and dealing with sequences and series is the same thing. So why are we even dealing with it twice? Well, for some peculiar reason, whether this reason is psychological or not, we can get a lot more results conveniently, or results written conveniently in terms of series rather than sequences. And therefore, convergence of the series, that probably students hate more than convergence of the sequence, in professional mathematics give us much more results than convergence of the sequences. Just one more remark about general series, that while you may not realize it, but all your life you've been dealing with the series. So for instance, if you take some number, e square root of 2 pi, whatever the number you want, you know that you can write them down in decimal expansion. In other words, any one of those numbers is equal to, say, I don't know, 3.12579 etc. Okay, infinite expansion of decimal expansion of this number. And what are you writing when you're writing this particular thing? Well, you are writing that x is equal to 3 plus 1/10 plus 2 over 100 plus 5 over 1,000 plus 7 over 10,000 plus etc. So in reality, when you are writing a decimal expansion of a number, you are writing it as a series. So this is just one application of the series, or one way to look at the series, that you've really been dealing with it all your life just without knowing it. Okay, so that's a short introduction to the notion of series, and now let's start doing a little bit of mathematics. So I'm going to repeat what I said before. I'm trying to position this paper correctly. I'm going to repeat what I said before, that if I have the series sum of ck, k from 0 to infinity, then the series converges if and only if the sequence Sn, so this is a sequence of partial sums, converges, and that happens to be if and only if the sequence Sn is a Cauchy sequence. Cool so far? Okay. And that happens to be if and only if, remember what was the Sm minus Sn? So Sm minus Sn was defined to be the sum of ak, k from n plus 1 to m, and these have to converge to 0. And these have to converge to 0 as n and m tend to infinity. Okay, so the convergence of the series is equivalent to convergence of the partial sums, which is equivalent to this particular kind of sums convergent to 0. And this should be true for any n and m. So in particular, if you take m is equal to, say, n plus 1, then this term over here will simply tell you that a n plus 1 converges to 0. Okay, so what is the conclusion? The conclusion is that if... okay, so this was the series ak in this case, okay? So the conclusion is that if the series sum of ak converges, then the terms of the series, let me write it down the terms of the series an must converge to 0. Okay, this is a necessary condition, but not a sufficient condition. So if you happen to be dealing with a series, you're going to look at the terms of the series. For instance, if you're dealing with the series that I dealt before, minus 1 to the power k, the terms of the series is equal to minus 1 to the power n. This does not converge to 0, and so the series diverges. Now, unfortunately, or fortunately, depending on your point of view, this particular condition is necessary but not sufficient. Later on, we're going to show something that I'm sure you already know from your other classes, like Calculus 2, that if I look at the series of the form 1 over k, so this is 1 plus 1/2 plus 1/3 plus etc., in this case k starts from 1 to infinity, then the terms of the series, the Cn here, is equal to 1 over n, and it converges to 0, but, and we haven't proved it yet in this class, but we will, but the series 1 over k diverges. Okay, so let me repeat it again, that this condition, that the terms of the series tend to 0, is a necessary condition and not sufficient condition. And again, looking ahead at what I'm going to be doing, many of the things that I'm going to be doing can be reduced to the following sort of emotional, almost emotional thing. And the almost emotional thing in this case will be, okay, so suppose that Cn does not converge to 0, boom, we're done. The series diverge. Now suppose that Cn does converge to 0. The next question I'm asking myself in my mind, without making it out loud, how fast? And if the Cn converges to 0 fast enough, then this is C. Then it turns out that the series would be convergent, and if it doesn't converge to 0 fast enough, then the series will be divergent. This is just an emotion for now. I'm going to put more sense into this emotion later on, but for now I'm just telling you what to expect. Okay, so it's time to start proving a few theorems here. And the first theorem I'm going to state in Calculus 2 form, or maybe not, I don't know. The first theorem I'm going to state is the following theorem. If you have the series Ck and you compare it to another series, so consider the series Ck with absolute value, so the difference between the terms of the series Ck and the terms of this series is the terms of this series are all positive and the absolute value of the series. Now the theorems that I'm going to state is if this series converges, so this is a series with absolute value of the terms converges, then this series converges. Okay, let's prove this theorem. And to show you how convenient and how beautiful this tool of Cauchy sequences is, let me compare the partial sums of the series Ck and the partial sums of the series Ck with absolute value. So let's suppose that Sn be partial sums for this series, and let's suppose Tn be the partial sums for this series. Then remember Sn minus Sm, or Sm minus Sn, must converge to 0. This is the Cauchy criteria, and this will be equal to the sum of ck, k from n plus 1 to infinity to m. Alright, now on the other hand, Tm minus Tn is equal to the sum of ck with absolute value, k from n plus 1 to m. And of course, all the terms with absolute values of ck are positive, so I can just write it down as the sum k from n plus 1 to m of ck. And now we're going to use triangle inequality. By triangle inequality that we studied in the very first chapter, not in the second chapter, because we're just dealing with numbers, Tm minus Tn, sorry, let me try it again, Sm minus Sn, this is equal to the sum. Now this is a normal sum, there is nothing crazy about it, because it's a finite sum, and so this is less or equal than the sum of ck absolute value. Remember, this absolute value of the sums is less or equal than the sum of absolute values. And what does that mean? That means that this is equal to Tm minus Tn. So if this thing converges to 0, that means that this thing converges to 0. And so we proved the theorems that we wanted to prove. The fact that this thing converges to 0 means that the series with absolute value converges. The fact that this thing converges to 0 means that the sum of ck converges, and that is one of the great accomplishments. Let me tell you one more principle which will be important as we go on, and that is particular case if the series ck, k from 0 to infinity, consists of numbers ck which are all positive. In other words, my series consists of terms which are all positive. There is no negative signs there. Well, remember that the series converges if and only if the sequence of partial sums converges. So the sequence of partial sums here will be equals to C0 plus C1 plus C2 plus etc. plus Cn. And what will be the next partial sum? Sn plus 1. Well, it will be C0 plus C1 plus C2 plus etc. plus Cn plus Cn plus 1. Good? Now remember that this Cn plus 1 is a positive number or non-negative number, which means that Sn plus 1 is greater or equal than Sn. In other words, in this case, when our series consists of positive numbers, then the sequence of partial sums have the property that Sn is less or equal than Sn plus 1. In other words, this sequence Sn is monotone, and thus, by the theorem from the previous section, converges if and only if it is bounded. That is, the numbers Sn are less or equal than some number m, which does not depend on anything. Okay, so one advantage is of dealing with the sequence of partial sums, that instead of real convergence, all we have to do is we have to check boundedness. Now, at least one way of dealing with the sequence without partial sums consists of using the previous theorem. I take the series with arbitrary terms, and then I'm going to put absolute value over the terms. So if this series converges, then this series converges, but the point is that this is a series with partial sums being increasing. In other words, the sequence of partial sums is monotone, and so this particular series over here converges if and only if the sequence of partial sums Sm are bounded. Okay, so I hope I'm not telling you anything mind-shattering yet, and I'm going to tell you a few results that once again you probably know from Calculus 2, and I don't know if you proved it in Calculus 2 or not, but the results go as follows. It's called comparison tests. And the comparison test says that if you have two series, AK and the series BK, and both series are the series with positive terms. Now there are two parts to comparison test. One, if AK is less or equal than BK, so if the terms of the first series is less or equal than the terms of the second series, and if the series BK converges, then the series AK also converges. Part 2 says that if AK is greater or equal than BK, and if the series BK diverges, then the series AK also diverges. Okay, so these are two comparison tests that you probably studied in Calculus 2. There was another test the last time I taught Calculus 2, something about limit comparison test, but let me not go into it. So what I want to do is very, very quickly go through the proof of it. So case 1, proof. So let's suppose that Sn are partial sums for the first series, AK, k from 0 to n. And let's suppose again that Tn are the partial sums for the second series, Bk, k from 0 to n. Now remember that both of those series are series with positive terms, so to conclude that one of the series converges, all you have to do is to conclude that the sequence of partial sums is bounded. So let's suppose that the series AK converges. So k here goes from 0 to infinity. Now this means that the sequence Tn is bounded. Right? Remember, I don't have to put absolute value of it because all the terms are positive, and so Tn is also positive. But AK is less or equal than BK, and this implies that the sum of smaller numbers is less or equal than the sum of bigger numbers. So this means that Sn is less or equal than Tn. And since Tn is less or equal than m, that implies that Sn is less or equal than m, which implies that the sequence of partial sums for the first series are bounded, which means that the sequence of partial sums converges. Now, proof of 2 goes just about the same way. So let's suppose now that AK are greater or equal than BK, and let's suppose that the series BK diverges. Well, what does that mean? That means that the sequence of partial sums for the series with BK are not bounded. In other words, the sequence Tn goes to infinity if you want. Okay, so in other words, it's not bounded. It grows arbitrarily far. Now the sequence Sn this time is bigger or equal than the sequence Tn, because we assume that the terms of this series is greater or equal than the series Bk, and that means that Sn is greater or equal than Tn, and if Tn goes to infinity, then so Sn, and that implies that the series Sn diverges. Okay, so I'm looking at Rudin at this particular moment, and Rudin states one of the theorem in exactly the same way as I stated it. The other theorem he states a little bit different, and what he states is that if you have the series AK, and this time the series AK are not necessarily the series with positive terms. So AK are not necessarily positive. And suppose you have the series CK, and CK this time are positive, and you also know that AK is absolute value is less or equal than CK. Okay, so what he states is that if the series CK converges, then the series AK converges, and it will follow from everything I told you before. So let's see. We know that absolute values of AK is less or equal than CK, so CK are automatically positive, and that if the series with CK converges, then this series converges. And as I proved to you before, this implies that this series converges. Okay. Actually, there is something important here that Rudin postponed this discussion for a little bit later. Maybe I will do two, but it's just a term. So the point is that if the series AK converges, then we say, then you know that the series AK converges, but we're usually adding one more word for a reason that will be explained later. The series AK not just converges, but converges absolutely. Okay, I'm just giving you a heads up on this new terminology. Good? All right. So, here's my next task. I proved those comparison tests, right? I proved this theorem that I have the series AK and the series BK, and I know that if this is a series with positive terms, and AK is, say, less or equal than BK, the series BK converges. Then the series AK converges. Now remember, that's the case when AK and BK are greater or equal than 0. Oops. This is better, right? Okay. Now, there is a divergence test. So now here's an idea. Suppose I have some series, let's say the series AK, and I would like to decide if this series converges or diverges. Well, I don't know. It's a little bit difficult for me to write down the partial sums for this series, but what may be a good idea is to have another series for which the partial sums are written rather easily and decide if that series converges or diverges, and afterwards, if this condition is satisfied, then boom, you will say, okay, so therefore this series converges. And the first series, and probably the only series, for which we can write the sequence of partial sums rather easily, is the geometric series. So x is a number, in this particular case, and I'm going to look at the series x to the power k, k from 0 to infinity. And what is it? It is 1 plus x squared plus x cubed plus x to the 4 plus etc. So this is an infinite series, and I want to decide if the series converges or not. Now, the advantage of this particular series, and this is why I would like to study them, is because this is the only time in my life when I can write the partial sums for this series explicitly. So you probably know this formula. that Sn, which is equal to 1 plus x squared plus etc. plus x to the power n, and this is equal to 1 minus x to the power n plus 1 divided by 1 minus x. Now, for those of you who know this formula, good. You can skip the next 2 seconds of my presentation. For those of you who don't, just very quickly, take 1 plus x squared plus x to the n, multiplied by 1 minus x. So what are you going to have? You're going to have 1 plus x squared plus etc. plus x to the n. That's what happens if I multiply this term by 1. And when I multiply it by x, I will have minus x squared minus x cubed minus etc. minus x to the power n plus 1. So this x and this x cancel each other. This x squared and x squared cancel each other. Everything cancel each other. And this is equal to 1, and the last term here will be minus x to the n plus 1. In other words, the product of these two terms is equal to this, and this is where this formula comes from. Okay, so now for this geometric series, as I wrote it, you have an explicit form of partial sums for the series Sn, which is equal to 1 minus x to the power n plus 1 divided by 1 minus x. X is a fixed number. And for a moment, I'm going to deal with a case when x is equal to 1, but for a moment, suppose x is not equal to 1. So this is an exact fixed number. Agree? Okay. So, when is Sn converges? Well, Sn definitely converges if x in absolute value is less than 1. Why does it converge if x is less than 1? Well, we know from the previous discussion that this term over here, if x is less than 1, tend to 0, and so in this case, not only we know that Sn converges, but we know exactly what it converges to. It converges to 1 minus x. Now, what happens if x is greater than 1? Well, if x is greater than 1, then this term over here goes to infinity. In other words, this sequence diverges, and so the whole sequence diverges, and so the conclusion is the series diverges. Finally, if x is equal to 1, right, then the terms of the series, being positive or negative, I don't care, x to the n definitely does not go to 0, and therefore the series diverges. All right. Are we good? Okay. So at this particular point, let me make the last comment, and that is, remember how I told you that if I look at this series, minus 1 to the power k, the series diverges, but if somebody puts a gun to your head and doesn't allow you to give an answer diverges, the best possible case you can give is the case that it converges to 1/2. Don't ever do it on a test, don't ever do it in mathematics class. It is only in case of emergency. So let's see. Let's suppose that I have the series Sn, or S, which is equal to the sum of x to the power k, k from 0 to infinity. Again, this is 1 plus x squared plus x cubed plus etc. So this is a infinite series, and let's suppose that x is a little bit greater than minus 1. So x is equal to like minus 1 plus epsilon, right? Well, if x is equal to minus 1 plus epsilon, and epsilon, of course, is a little tiny itsy-bitsy positive number, in that case, absolute value of x is less than 1, and the series minus 1 plus epsilon to the power n will converge to what? Well, it will converge to 1 over 1 minus x, which will be 1 over 1 minus 1 plus epsilon, which will be 1 over 2 minus epsilon. And so now you say, something that you are not allowed to say really. If epsilon tends to 0, then the series will come closer and closer and closer to 1/2. In reality, they don't. They will diverge. But again, 1/2 is the most reasonable answer that you can give to this question if your life depends on it.